All right, this is going to be our walkthrough for the homework assignment titled Fundamental Theorem of Calculus. And so for each of these, we're going to be just asked to find the derivative of the integral of some function, right? And so this is pretty common to see at least one or two questions like these on the AP test. You might get one as easy as this first one, right? That's just asking for the derivative of the integral from 2 to x of sine squared t cosine t dt. So there's multiple ways to look at this, but I think the easiest way to look at it is, suppose we have capital F as an antiderivative of sine squared t cosine t. And then if that was the case, then I would know that function, right? That what we're looking at here is the derivative with respect to x of the antiderivative of that function, sine squared t cosine t, evaluated at x, minus that antiderivative evaluated at 2. Well, that antiderivative is just capital F, so it's the derivative with respect to x of capital F of x minus capital F of 2. And of course, the derivative of capital F of x is just our original function evaluated at x, so sine squared x cosine x. And the derivative of any function evaluated at 2 is just 0, right? Because any function evaluated at 2 is just a constant. And the derivative of a constant is, of course, just 0. So our answer should just be sine squared x times the cosine of x. We've essentially just got the same thing going on here, right? We want the derivative with respect to x of an integral from a constant to x of this function. So if capital F is an antiderivative of e to the t cosine of t squared, then this should be the same as the derivative with respect to x of capital F of x minus capital F of 0. And again, capital F of 0 is just a constant. And so the derivative of a constant should be 0. And the derivative of capital F at x should just be the original function evaluated at x, e to the x times the cosine of x squared. Now this one is a little more complicated because it's a constant to x squared. Right? It's no longer a constant to x in the integral. It's a constant to a function. We can approach it the same way, that if capital F is an antiderivative of t squared minus e to the 2t, then this should just become the derivative with respect to x of capital F of x squared minus capital F of 2. And again, capital F of 2 is a constant, and its derivative should be 0. But when I take the derivative of capital F of x squared, I have to actually use the chain rule, right? Because this is a function within a function, right? So the derivative, I'm going to write this off to the side here. The derivative of capital F of x squared is actually f prime, capital F prime of x squared, times the derivative of x squared, times 2x. So this should equal 2x times my original function evaluated at x squared, which would be x squared squared minus e to the 2 times x squared. And so, of course, that'll simplify down to, this is 2x times x to the 4th, or 2x to the 5th, minus 2x minus 2x e to the 2x squared. All right, for our next one here, again, this is a constant to a function. We'll do the same process. If capital F is an antiderivative of t cubed cosine t, then this just becomes the derivative with respect to x of capital F of sine x minus capital F of 1. Now again, the capital F of 1 is a constant. Its derivative is 0. And if I take the derivative of capital F of sine x, that should be capital F prime of sine x times the derivative of sine x, which is cosine x. So that becomes my original function evaluated at sine, and then times cosine. So I have cosine x, and then my original function evaluated at sine is sine cubed of x times the cosine of the sine of x. All right, for our next one, again, we'll let f, capital F, be an antiderivative of t cubed minus t squared. And what this then ends up becoming is the derivative with respect to x of capital F of x squared minus capital F of x. No constants this time, right? But the derivative of capital F of x squared ought to be f capital F prime of x squared times 2x. Right? And this is just capital F prime of x, which is just our original function evaluated at x. So what we end up with is 2x times my original function at x squared, so x squared cubed minus x squared squared. And then that is minus my original function at x, which is x cubed minus x squared. We should be able to combine the like terms, right? X squared cubed is x to the 6th, so this becomes 2x to the 7th. And then we've got, this is minus x to the 4th, so minus 2x to the 5th. And then a minus x cubed and a plus x squared when I distribute that minus sign through. We've got two options here. One option is to just do the same process we've been doing. Or the other option is to flip the limits of integration first and then make it negative. So if you want to flip the limits of integration so we have a constant to x in the integral and then do that process, you can. I'm just going to leave it as is. I'm going to say if capital F is an antiderivative of cosine 2t minus t, then what we've got is the derivative with respect to x of capital F of 7 minus capital F of x. Well, capital F of 7 is a constant, and if I take its derivative, that's 0. So really all I'm left with is the opposite of the derivative of capital F at x. Well, the derivative of capital F at x is just my original function at x. So what we end up with is a positive x minus a cosine of 2x. All right, our next one here, we've got x cubed to 3, right, for our integral. We'll do the same thing. Capital F is an antiderivative of 3 to the t minus sine of t, which then gives us the derivative with respect to x of capital F of 3 minus capital F of x cubed. The capital F of 3 part is, again, a constant, so its derivative is 0. And if I take the derivative of negative capital F of x cubed, I'll have negative capital F prime of x cubed times the derivative of x cubed, which is 3x squared. So what we end up with is negative 3x squared times my original function evaluated at x cubed, which will be 3 to the x cubed minus the sine of x cubed. And that should be our final answer. All right, just a couple more of these to go. So for this one, we'll do the same thing. We're going to let f be an antiderivative, capital F, be an antiderivative of tangent. So what we've really got is the derivative with respect to x of capital F of 3x squared minus capital F of 2x. Well, the derivative of capital F of 3x squared ought to be the derivative of the 3x squared, so 6x, times the original function evaluated at 3x squared. And then the capital F of 2x, its derivative should just be the derivative of 2x, so 2, and then the tangent of 2x, so minus 2 tangent 2x. And that's our final answer. All right, our last one here. We'll do the same process. We'll let capital F be an antiderivative of e to the t squared. This becomes a derivative with respect to x of capital F of e to the x minus capital F of x squared. And of course, the derivative of capital F of e to the x will be done with the chain rule. So that'll be the derivative of e to the x, which is e to the x, times the original function, e to the t squared, which we'll evaluate at e to the x. So e to the x squared. And then minus the derivative of x squared, which is 2x, times the original function evaluated at x squared, which will be e to the x squared squared. And if we simplify this down a little bit here, we can get e to the x times e to the 2x, right? E to the x times e to the 2x, and then minus our 2x e to the x to the 4th power. And that should be our final answer here. And if you want to, you could, we have e to the x times e to the 2x. You could add those together as one exponent if you wanted to, but that's not necessary. And that's the end of our walkthrough here on our fundamental theorem of calculus homework assignment.